Homework 3.4, the rational zero theorem, zeros of polynomial functions, video 9. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. This last video will pertain to questions 15, 16, and 17. But before we get to using the linear factorization theorem, I need to not really warn you, but just let you know about something in the homework. Throughout all these videos, I've been using the word zero to represent a value that makes a function equal to zero, which is a correct definition. However, there's a synonym for the word zero, the word root. So anywhere in the homework where they say root, you can treat it like the word zero. Technically speaking, they shouldn't be using the word root. A root is a solution to an equation. A zero is a characteristic of a function. But I won't begrudge the author that oversight because it's a very common thing to do, and perhaps I'm incorrect, but in your homework, if you see the word root, it is a synonym for the word zero. So anywhere you see the word root, you can just pretend it says zero. All right, so let's use the linear factorization theorem. We're going to find a polynomial function that satisfies some given requirements. Requirement number one, the degree equals 3. So the highest power would be x to the third power. 4 and 2i are zeros. So if we put the function equal to 0 and solve it, one of the solutions is 4, one of the solutions is 2i. And f of 1 equals 30. This is what's called an initial condition. For those of you going down the calculus, physics, or engineering path, you will often encounter problems where you have an initial condition. Initially, my function must do this. Actually, all of these would be considered initial conditions. So how do we do this? Well, we use the linear factorization theorem and the complex zero theorem. The linear factorization theorem says that every zero is a factor, essentially. So if x equals 4 is 0, that implies that x minus that, so x minus 4 is a factor. We did that already. We did that way back at the beginning of this series. Now, x equals 2i as a 0 actually implies two things. As a consequence of the linear factorization theorem, honestly, it's just the factor theorem. Every zero comes from a factor. Then x minus 2i is a factor, which is a weird-looking factor, but it is correct. But this isn't the only thing that this tells us, because the complex zero theorem, the one that says if a plus bi is a factor, then so is a minus bi, any complex factor, any non-real factor, any non-real zero has a conjugate companion, if you will. So if a plus bi is a 0, so is a minus bi. So how does that pertain here? Well, 2i doesn't look like it has this form, but it does. Remember, every number is a complex number, even this guy, because he's positive and its real part is 0. So if 0 plus 2i is a 0 of the function, then so is 0 minus 2i. But that 0 isn't necessary either. So the complex zero theorem says, since you're a 0, then so is x equals minus 2i is a 0. And what does that tell us? That tells us that x minus this is a factor. So x minus negative 2i would be x plus 2i. And what else do we know? The degree is 3, and the linear factorization theorem also says that whatever the degree is, that's how many factors you should have. 1, 2, 3. So what does this mean? This means that our function has this form, according to the linear factorization theorem. Some constant that we don't know yet times the product of the factors. Now I'm about to erase everything here and move this up, because I'm going to need the space. But when you're given zeros, you are given factors. And when you're given a complex zero, you're given another complex zero, and hence another factor. Glue them all together, throw some unknown constant in front, and you've got your function. But two problems with that answer. Number one, that doesn't look like a polynomial function. It is, it's just factored, and we don't want it that way. And number two, what's up with that a in front? What's that number supposed to be? Well, that's where this initial condition will come in. Now, before we get to it, let's take what we currently have and see how far we can multiply it. Now, you may not be accustomed to foiling out problems involving i's. I take that back. In the very first homework assignment, we multiplied complex numbers. So yeah, we have been down this path before, it just didn't have x's here. When you're multiplying these out, it's a good idea to multiply the ones involving the conjugates, because when you do, things get real pretty. So we're going to start out by foiling this one, and I'll take it slowly since it's got i's. X times x is x squared. X times positive 2i is positive 2ix. Negative 2i, yeah, that's the correct thing to write, positive 2ix. I know it looks really crazy. Negative 2i times x is negative 2ix. And then for the last part, take it slow. Negative times positive is negative, 2 times 2 is 4, I times I is I squared. And we still have this guy over here, and that guy. So everything else is still sitting there. So this looks messy until you look a little more closely and notice two things. Number one, the middle terms cancel. Hooray. And number two, I see an I squared. And do you remember what an I squared becomes? Recall that I squared becomes negative 1. So this becomes negative 4 times negative 1, which makes it a positive 4. So our function now has the form a times x minus 4 times x squared. These cancel, and this becomes a positive 4, and suddenly things look better. I'm still going to FOIL it, because I want this to look like a polynomial function, not something that's already factored. The a's still there, we're about to get to it. If we FOIL this out, and I'll just spare you the details, we'll get x to the third power minus 4x to the second power, that's the inside product, plus 4x, that's the outside product, minus 16. I don't know why I closed parentheses prematurely. I always have to erase them and draw them again. The only reason I did FIOL was to put them in decreasing power. Now, could we distribute the A? Well, we could, but I'd like to know what it is first. So how do we figure out what the A equals? That's where we use our initial condition. Because I know two things about putting in 1. Number one, it should equal 30. And number two, can't I just put the 1 there? That's f of x, right? So putting 1 means I can put it over there. So if I put in a 1, and where there's an x, I get 1 to the third power minus 4 times 1 squared plus 4 times 1 minus 16. So I'm going to have to work all that out. So 30 equals a times some number. Well, this is 1. Let's write this in a different color. 1 minus 4 plus 4 minus 16. Well, the 4's cancel, and 1 minus 16 is negative 15. Now I can solve for a. The only reason it's not by itself is because it's multiplied by negative 15. But if I divide both sides by negative 15, and thankfully it divides evenly, I'm pretty confident in these questions it will divide evenly here, we get a equals negative 2. So we found the missing piece of the function. So now we can take that and put it back over here and say f of x equals negative 2 times x cubed minus 4x squared plus 4x minus 16. And finally, we can distribute and get negative 2x cubed plus 8x squared minus 8x plus 32. And there's our function. It's a third-degree polynomial. When I put in 1, I get out 30. You may want to verify that, but it's pretty easy. You put a 1 here and here, the 8's cancel. Put a 1 here, you get negative 2. Negative 2 plus 32 is 30. And if we were to find its zeros, by listing possible rational zeros, using synthetic division and all that jazz, we should get 4 and 2i, and also negative 2i. So building the function back up from its zeros is actually pretty straightforward if you know that every zero has a factor. Every zero has a factor. Even the implied zeros have factors, and you're not afraid to bust it all open. Really, the only new thing here is how to find this unknown numeric constant factor in front, but that's just taking advantage of the initial condition and the function that you almost finished building, and then solving for that missing constant. Put it back in, distribute, and it's all good. And all three of these are just like this one. I do want to warn out, just for full disclosure, I do want to warn you, for full disclosure, that this problem could have been a lot worse, because not all complex zeros are just imaginary. So for example, it could have said 1 plus 2i is a 0, which would imply that so is 1 minus 2i. But the hard part about that is that when you set up the factor, you have to set it up like this. 1 minus the 0, distribute the negative. That's the easy part. Then the foiling gets bigger because they're trinomials instead of binomials. Luckily, none of your homeworks go down that path. So if you kind of follow the previous example before I change this, you should be good. And that's the last video of this section. One more section to go before we end test 3 material.